So today we're going to look at geometric sequences and determine how those are the same and or different from arithmetic sequences. So a geometric sequence is just an ordered list of terms with a common ratio. So this is different than arithmetic sequences. Arithmetic sequences had a common difference. So arithmetic sequences are like linear functions. There's a constant rate of change, that common difference. Whereas a geometric sequence is like an exponential function because you're multiplying by a common ratio r every time. So r is just whatever the common ratio is, just like when we were studying 2 to the x. So the equation y equals 2 to the x, 2 is the common ratio. You're multiplying by 2 each time. Or 3 to the x, you're multiplying by 3 each time. So just like arithmetic sequences had a closed and recursive formula, which is a pattern that you're going to use every time, for a geometric sequence, it's a sub n, it's your first term times the common ratio, n minus 1 times, and this is in the exponent, so it's like an exponential function. Whereas when we were talking about geometric or arithmetic sequences, it was that you take your first term and you add your common difference n minus 1 times. This is taking your first term and multiplying by the ratio so many times in the exponent, because that's multiplying. And the recursive formula is that, how do I get the term I want? I take the term before it. So I'm just using a sub k to represent the term I'm on, and k minus 1 represents the term before it. Multiply by the common ratio, and I have to tell the reader what my first term is. So start at 6 or start at 8. So if this is my sequence, 4, 8, 16, and 32, to write that using the closed formula, it would be a sub n equals my first term, which is 4. What's happening to the 4? It's being multiplied by 2, n minus 1 times. So the n minus 1 is a superscript. So if I just checked, can I generate the third term, which is 16? 4 times 2 raised to the 3 minus 1 power. So that would be 2 squared, which is 4, and 4 times 4 is 16. Just make sure you did it right. Recursive formula, a sub k equals a sub k minus 1 times 2, right? I'm multiplying by 2 every time. Take the term before it, multiply by 2. And I need to let the reader know that they need to start at 4. So start at 4 and multiply by 2 every time. So that would be the closed and recursive formula for this sequence right here. So example 2 says, find the common ratio between these geometric sequences and then use the formula to find a sub 6, so the sixth term. So let's see, it looks like we're multiplying by 3, right, each time. So my closed formula would be a sub n is, I'm starting at 12, I'm multiplying by 3, n minus 1 power. And I'm going to plug in 6 over here, so that would be 12 times 3 to the 5th. So if I multiply 12 times 3 to the 5th, I get 2,916. So that was on my calculator. I did 2 times 3 to the 5th. So let's do the same thing here. What am I multiplying by to get from negative 1/3 to positive 1/9 and then to negative 1 over 27? Looks like the denominator is getting multiplied by 3. And to go from negative to positive, I must be multiplying by negative 1/3. Over here, the r value was 3. So a sub n equals, I'm starting at negative 1/3. I'm multiplying by negative 1/3 to the n minus 1 time. I could just write this as a sub n is negative 1/3 to the nth power, right? Because then squaring it gives me 1/9, cubing it gives me negative 1/27. But that only happens when your first term and your ratio are the same number. I'm trying to plug in the sixth term. So I'm just going to kind of cheat and use my simplified formula. So I've got negative 1/3, and that's being raised to the 6th power. So it's going to be a positive number. See how it's going negative, positive, negative, positive? So 3 to the 6th is, I don't know, 3 to the 6th is 729. So I must have positive 1 over 729 as my 6th term. All right, so this is just 3 problems that I wanted to do with you before you do the guided practice on the back of today's geometric sequences, and then jump over and turn that in using Google Classroom. So let's see, find the recursive formula for the geometric sequence. So the first term is 3, the common ratio is 2, and write out the first through 5th terms. So let's see, a sub k equals a sub k minus 1. It's a geometric sequence with a common ratio of 2. So I'm multiplying by 2 every time, and I need to tell the reader that the first term is 3. And then I need to write the first through the 5th term. So the first term we know is 3. We're multiplying by 2 every time. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And 24 times 2 is 48. So those would be my first 5 terms of the sequence. This next one, let's see. Find the closed formula. The first term is 20. The common ratio is 1.05, and then find the 15th term. So notice I gave you closed formula. That's going to help you find the 15th term. So a sub n, the first term is 20. It's being multiplied by 1.05 n minus 1 times. So I'm going to plug in 15. So that's going to be 20 times 1.05 to the 14th power on my calculator. 20 times 1.05 to the 14th power rounds to what? 39.6 about. Oops, here's what I got. All right, last question together, and then I'm going to leave you to do the guided practice on this back page. Actually, I might do the, maybe I'll do one of the application problems with you. Given the sequence, 5, 15, and 45, determine whether 3,645 is a term of the sequence and what term it is. So what I would do is I would write what this formula is. A sub n equals 5 times 3 to the n minus 1 power. So my first question is 3,645 even divisible by 5? 3,645 is divisible by 5. 3 to the n minus 1 power would have to be 729. So all I did was I set this equal to 3,645 divided by 5 on both sides. I know that 729 is a power of 3. I think we did that earlier, isn't it? 3 to the 6th? So if it's 3 to the 6th power, then n would have to be 7. Right, so that 7 minus 1 is 6, 3 to the 6th is 729. So yes, it is, and it's at n equals 7. Before you do the back page, because you're going to do the guided practice here, I wanted to just look at number 7, the idea of depreciation, because we haven't really talked about that as a rate of change when we did exponential functions. So a tool and die company buys a machine for $135,000. It depreciates at a rate of 30% per year. So it says, in other words, at the end of the year, the depreciated value is 70% of what it was at the beginning of the year. Find the depreciated value after 5 full years. So 5 depreciation. So it starts at 135,000 and depreciates 5 times. So in this case, you don't want to do n minus 1. You want to do 5 total depreciations. So your equation is going to be that you started at $135,000 and you're retaining 70% of the value. So it's worth 70% of 135,000 5 years later. So 70%, another 70% depreciation, another 70%, right? It's depreciating 30% each year and you're retaining 70%. And that could be tricky if you haven't done a problem like that before. So let's see, what is the value after 5 years? $22,000. Whoops, so 22,000, what is it? 689 and 45 cents is what it's worth after 5 years. So you are going to complete the guided practice on the back and submit that through Google Classroom.